A remarkably large number of practical problems have the characteristic that in performing an experiment there are only two possible outcomes. Now this kind of experiment is often referred to as a binomial experiment or sometimes as a Bernoulli experiment after the Swiss mathematician named Bernoulli. He studied the situation back in the 1600s quite extensively, and we build upon his work even today. Well, the binomial experiment has these characteristics. There are a fixed number of trials, and the number is designated with n. The trials are independent. The trials are independent. That is, the outcome of one trial has nothing to do with or is not affected by the outcome of a previous trial. The trials have exactly two outcomes. This is really the most important idea probably that defines or that begins the definition of binomial experiment. But two outcomes. Now they're often designated as S or F, success or failure. Now success doesn't necessarily imply good, and failure doesn't necessarily imply bad. It's just success in terms of the experiment that is underway. All right, success or failure. The probability of success is the same for each trial. And now usually in this circumstance we want to find the probability of R number of successes, of some particular number of successes out of the n number of total trials. Now all of this will be more understandable as we get into an example in just a moment. But first let's look at some notation involved. N will stand for the number of trials. Now remember, these trials have sort of a binomial outcome, either success or failure, but n is the total number of trials we're talking about. The probability of success will be designated with a p. Now there is an opportunity for confusion here, and particularly because of the way that I usually write. I have a habit of writing uppercase letters and lowercase letters in the same way. For example, here this is supposed to be a lowercase p. Here's an uppercase p. They look an awful lot alike. But this is the probability of S is a lowercase p. And the probability of failure is Q. Now, if we only have two possibilities here as success and failure, then P plus Q, you see it's a probability number, here's another probability number, and their total will be 1. So it's either success or failure in this kind of experiment. And R will be the designation for the number of successes that we have in n number of trials. Now, an example goes a long way to understand this whole idea. Suppose we are talking about a roulette wheel. A roulette wheel has 38 numbers, and 18 of the numbers are red, 18 are black, and 2 are green. Now, I think it's a little white ball is spun around the edge of the wheel and then falls into the wheel onto one of these colors. And so betting is done according to the expectation of where that little ball is going to fall. And suppose a gambler is betting on red, all right? And so the probability of success is the probability that a red comes up on the roulette wheel when the spin is made. And since there are 18 red spaces out of 38 total spaces, the probability of success is 18 out of 38, or 0.474. And that's the designation, that's what P is all about. Okay, so probability of success is P, and we've given it a number for this particular problem. Okay, probability of failure then would be the probability of not success. All the other numbers, you see, would be failures. So 18 from 38 is 20, so 20 out of 38 would be failures. And so that probability number is 0.526, and we designate that with Q. All right, so that's kind of the setup of what's going on. Now let's talk about the possible outcomes in this situation, and we want to figure some probabilities here. And we're flowing with a conversation here, and we're not going to come to any conclusions. We're just going to notice some things for a little while, and then we'll come to some conclusions sort of at the end of this little discussion. But here's the way we kind of start the idea. We have possible outcomes for remember, three plays now on this roulette wheel. And these are the outcomes of 3 plays. Now, this 3 plays, that would be the number of trials that we have. 3 then would be the N that we were talking about earlier. All right, now what are the possible outcomes? Well, we could have failure, 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 success, failure, success, failure, success, failure, failure, and so on. And these are all of the possible outcomes, all of the ways that this can happen. Now, notice that there are 8 of them here. We could have figured out how many there would be by thinking, well, let's see, on the first trial, how many outcomes are possible? 2, success or failure. On the second one, 2, success or failure. On the third, 2, success or failure. So it's 2 times 2 times 2, or 8 possible outcomes for 3 plays in this situation. All right, and these are all 8 of them listed. Now, I've put a probability number associated with each of these. And here's how those probabilities were calculated. Now, now notice that all of these 3 have 2 failures involved in them. And so they're all figured pretty much the same way. Let's come over here and make that calculation so you'll see why I got the 0.131 over there. It turns out that if we're thinking about, and I'm going to take, this is the long version, I'll show you the short version in just a moment, but the probability that we have an outcome of failure, failure, success is the probability of failure and, well, let me do it this way. My bad. I'm backing up a little bit. I want to get ahead of myself. The probability of failure and success is what this means. And now since these are independent trials, when we have the and, we can multiply probabilities. So it's going to be the probability of failure times the probability of failure times the probability of success. Now, probabilities are associated with success and failure, and these are those probability numbers down here. So the probability of failure would be, let's see, that's a Q, and this is a Q. And I could immediately put the numbers in here, you see, but I want to make sure we understand the difference in notation and that they're sort of interchangeable. The probability of P of F is the same as Q in both places, and P of S is the same as lowercase p. So either way we write this is okay. And now let's see, the Q is the 0.526, and this also is a 526, and the success is 474. And multiplying these, we find that the product is 131. All right, now that's what I found right here. Now all of these would be found the same way, and these will have the same number because there are 2 factors of F, you see, in all 3 of these, and 1 factor of S. So because the same factors are involved, they will have the same probability number. And in a similar way, all the others are calculated. Now, our interest is in the number of successes, or the number of failures possibly, but let's make a chart. Let's outline the number of successes here called R, and and consolidate. We're consolidating sort of what we have right here. That for R being the number of successes, no successes means, well, let's come back over here. That's failure, failure, failure. That was the 0.526 times 0.526 times 0.526 that gave 0.146. Okay, so that's over here. Now, probability of failure times probability of failure times probability of failure is Q times Q times Q, or Q cubed. Now, for one success to occur, let's see, one success, come back over here. all of these items have one success in them. All right, each one of them is 0.131. Now the probability that we're going to have one success is the probability of this one or that one or this one. And adding these three then, we would get the 0.393. The calculation for this could be made as, since we have three items that all involve these factors, you see, then we could make the calculation directly like this if we knew ahead of time that there were going to be three of them. So 3pq squared gives that. And p has a value, q has a value from over here. All right, now for two successes involves, well, let's see. This has two successes in it. This has two successes in it. Here we have two successes. All three of those have the same probability of 0.118. If we add those together, we get 0.354. And a way to calculate 0.354, since there are three of them and there were two successes and one failure, it's 3 times p times p times q. All right, in order to calculate that. That is a way of doing this rather quickly. All right, and the three successes would be p times p times p, or 0.106. Now, with this information, we could make some calculations. We could calculate, for example, what's the probability that we're going to have exactly two successes? Well, the probability of exactly two successes we can read right off of the chart here. It's 0.354. And that probability could be 35.4% if we want to change it into a percent. Okay, fine. Now, what's the probability of more than one success? More than one success. That would mean two successes or three successes. How do we figure that? Well, let's see. More than one would be two or three successes, so we could add these two probabilities and have the probability of more than one success. How about the probability of at least one success? Okay, the notation for something like that is this. The probability for at least one success would be the probability that R, the number of successes, is greater than or equal to 1, at least 1. And this then would be, and we can take the long way around this, or we can take kind of a shortcut, but the shortcut version is that the probability that R is greater than or equal to 1 would be the sum of the probabilities of R being 1, R being 2, R being 3. And these are those probabilities. So it turns out to be and that sum turns out to be, so in 3 trials of a roulette wheel, if you're betting only red, are we betting red? Yeah, we're betting the red. If we're betting only red, the probability of having one success in 3 trials is 85.3%, or 0.853. Suppose we change the situation, and instead of 3 trials, we're talking about 4 trials. Now, how many outcomes would there be in 4 trials? Each trial now has 2 possible outcomes. So for the first trial, 2 possible outcomes. Second trial, 2 outcomes. Third trial, 2 outcomes. Fourth trial, 2 outcomes. 2 times 2 times 2 times 2. 16. So there are 16 outcomes when we have 4 trials. It's actually 2 to the 4th power, you see, as the number of outcomes. Now, I've listed those outcomes here, and I took a lot of time to do it, so let's admire it just for a moment. The thing we want to notice is this, that there's only one item that has failure, 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 and one item that has success, 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 success. All right, the others are those are one-of-a-kind items. Now, the other items have several involved that are pretty much the same. Here, this item has one success, one success, one success, one success. All of these, then, have one success involved. Now, these three have two successes, and these three have two successes. So there are 6 of them that have 2 successes. These 1, 2, 3, 4, these 4 items, now there were 4 over here that had 1 success. There are 4 over here that have 1 failure, or 3 successes. So these have 3 successes. Now, I want to show you that in the pattern of outcomes because it allows us then to make a chart like this over here where the successes are. We want to make a chart of the number of successes and the probability associated with that number of successes. If we're talking about no successes, then it means failure, 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 or Q times Q times Q times Q, Q to the 4th. Now, for one success to occur, remember there were 4 items over here that had only 1 success. So it's 4 times this 1 success, 3 failures. So it's 4 times P times Q cubed. And then for 2 successes, there were 6 of them over here. So it's 6 of them with 2 successes. If there are 2 successes, there are 2 failures. So we have P squared Q squared. And then for the 3 successes, that means 3 factors of P, 1 factor of Q. There were 4 of those items, so it's 4 times this. And then the 4 successes, there would be P times P times P times P. All right. I want you to notice something in this pattern, and we want to concentrate on this pattern in just a moment. We're going to make a calculation given this information in a minute too, but this pattern is quite interesting, and it follows a pattern that you may have already studied if you've studied college algebra and the binomial expansion. The pattern is this, that let's ignore the coefficients just for a moment and look at exponents. This exponent is 4 for Q, and then there is a P with Q cubed. The sum of these exponents is 4, and in the next one, P squared, Q squared, the sum of the exponents is 4. P cubed, Q to the 1 power, the sum is 4, and then P to the 4th power. All right, so in all of these, the sum of exponents is 4. That's one interesting thing. Another is this, that we start with Q to the 4th, and then we have Q cubed, Q squared, Q. You see the exponent on Q is decreasing by 1 each time, and we could even think that here it's Q to the 0 power if we want to just continue the pattern. And in a similar way, the factors, or the exponent on P is increasing. We could think of P to the 0, P to the 1, P squared, P cubed, you see, and then P to the 4th power. All right, so just notice that pattern here. Now, let's think for a moment about a calculation involving what we have here for the probability of some number of successes. Suppose P, the probability of success, is 0.8. And we want to find the probability that the number of successes is exactly 3. Exactly 3. All right. Then we would use from over here, from the chart, exactly 3. We calculate by multiplying 4 times P cubed times Q. Now, what is Q in this circumstance? Well, if P is 0.8 and we know that P plus Q is 1, then Q must be 2/10. All right, now with that information, we know that the probability is figured this way from over here, and so it's 4 times P is 0.8, and that's cubed times 0.2, or this is the probability. So we can make that kind of calculation knowing that we have this probability of success chart. Now, it's going to help you in a little bit. We're going to talk about a table in the back of your textbook that will give the information that's appropriate here. But we're developing the conversation a little bit, hopefully so that you will appreciate and remember how the binomial experiment and the formulas associated with it sort of come about. All right, let's talk about 10 trials. Now, if we're talking 10 trials, I can't possibly list all of the outcomes here on this one single 16-foot chalkboard. There are, in fact, 2 to the 10th outcomes for 10 trials. So we're not going to try to designate the number of outcomes. But if we don't have all of the outcomes listed, then how do we know the coefficient number associated with this p squared q cubed kind of arrangement? That's what we want to get to in just a second. All right, we do know this much, though. We know that if we talk about successes in 10 trials, then the number of successes could be 0, 1, 2, 3, all the way through 10. All right, so, and I have that here, and the dot, dot, dot means and so on down to 10. Okay, the probability of this number of successes, well, it's pretty easy to tell. For 0 successes, it means we have all failures. So it would be q to the 10th power. Now, if we think about that pattern that we started earlier, then the number of successes and failures over here, the total number will be 10. And if we have 1 success, we have 1 factor of p. And the rest of the factors are q's, failures. So for 2 successes, we have 2 factors of p and 8 factors of q. For 3 successes, 3 factors of p, 7 factors of q, and so on. Okay, so that's how we can establish this part of, or the letter part of our probability table for the successes. Now, what about these coefficients? It turns out that we can actually make the calculation of those coefficients. And as I mentioned before, this corresponds well with the binomial expansion. If you recall that, well, you may, I'm going to assume you don't recall that from college algebra, but you may have been exposed to it before. And it also corresponds with the numbers that are involved in Pascal's triangle. That's what I really love about mathematics, is that something that you learn way over here is applicable to something that you learn way over there. And so it all kind of fits together in one way or another eventually. Well, let's talk about the binomial expansion, and I will, hopefully I'm just refreshing your memory, but if we have x plus y to the 10th power, this is what it means by binomial expansion. We're taking this binomial to a certain power and we are expanding it, binomial expansion. Okay, we start out with x to the 10th power. The next term involves x to the 9th power with the first factor of y, and the next one involves x to the 8th power with another factor of y, 2 factors of y, and then x to the 7th power with 3 factors of y. And notice that in every case the sum of the exponents is 10, the same as our expansion exponent. And that's the pattern that we saw here earlier. Now, what about the coefficients? And the coefficient part is what we're concentrating on now. It turns out that the coefficients are calculated as a combination, and we can use the combination formula to calculate each one of these. This one is the combination. I'll write it underneath because I don't have quite enough room right here. This is the combination of 10 things taken one at a time. That is the way that we're going to look at it here. There is some symmetry in this binomial expansion, and the coefficient on the second term is the same as the coefficient on the second to last term. And when you learned this in college algebra, you learned this as the combination of 10 things taken 9 at a time, and that's the same thing as 10 things taken 1 at a time. So it's just a matter of fitting a certain kind of pattern. Now, in college algebra, when you learned about this, you used the 9 because the 9 happened to be the exponent on the first variable. But if you use the combination of 10 things taken 1 at a time, that would be okay. You could target either one of the variables, you see, the exponent on either one of the variables to figure your combination. And we're going to target a particular variable in what we're doing too, because this combination idea applies the same way over here. And so this is, you know, I'm going to simply use, well, it doesn't matter which one I use, and I'm trying to choose one. You see, the situation is this. Come back over here just for a second. This is going to be the combination of, the easy way to remember it is the combination of 10 things taken one at a time, because we're targeting the exponent on the p. You see, and it's the first one that occurs, and they go consecutively larger as we go down. So it's just easier to do it that way. Now over here we have an exponent that's decreasing every time. You see, so that's the difference in these two kinds of patterns, and maybe the need for looking at a different kind of pattern over here than over there. But it's the same idea that we had here, that we're looking for a coefficient of a particular term, and the sum of the exponents turns out to be consistent throughout the pattern, just as it is here, and all we're doing is identifying a coefficient by using a combination idea. Now here it's the combination of 10 things taken 2 at a time. Here the combination of 10 things taken 3 at a time, and so on as we go to the bottom of the pattern. So the 10 is the number of trials that we have. The 4 is the same as the exponent on p. So that's how we can recognize what we use for our combination idea. For example, if we wanted to find the coefficient in something like this. Now, even if we didn't know how many trials there were, if we had this facing us, we would know that 6 plus 4 is 10. There are 10 trials. So the coefficient then is the combination of 10 things taken, let's see, the exponent on p is 6. So the combination of 10 things taken 6 at a time. All right. And that combination, if you recall, it was the combination of 10 things taken 6 at a time is 10 factorial over 10 minus 6 factorial times 6 factorial. And it turns out, by doing it by hand or punching it into the calculator or whatever, it turns out to be 210. Before I go on with the next problem or two, I don't want to fail to mention, I don't want to forget that this idea of binomial experiments can apply to some problems even though the problem does not meet exactly the requirements of binomial experimentation. That is, one of the requirements was that every event was independent. And that's nice, and that's the way it's supposed to be, and technically that is the way the definition runs. But if the sample size is small relative to the population, it turns out that replacement, or this idea of independence, is not an absolute necessity. For example, if we're looking for 60 items out of 10,000, let's say, if there are 10,000 ping pong balls and 60 of them are painted red and the rest of them are white, what's the probability of getting a red one? Now, it's either red or not red, so it's a binomial experiment. And so the probability of getting a red, now let's say we're talking about 10 trials. On the first trial, the probability of getting a red ball is 60 out of 10,000. And then if we don't replace that first ball after it's drawn, what's the next probability? You see, the next probability is, gee, if one of the red balls was drawn out to begin with, we only have 59 left. But it's 59 out of 9,999. And those two, that 60 out of 10,000 on the first ball and the 59 out of 9,999, those probabilities are very, very close to one another. So it's the idea, and you may not remember this, and it's okay if you don't. It might come back to you sometimes when you talk about this in the future, or you have a particular binomial experiment and you say, it doesn't quite fit the criteria. Well, it's okay if it doesn't fit every part of the criteria if the sample is relatively small compared to the population. That is, if the population is really, really big and the sample size is relatively small, then we don't have to have this total independence involved from one trial to the next. Anyway, okay, let's get on with the matter at hand. Let's suppose we have 10 trials, P is 0.7. We want to find the probability of R being 4. Now remember, R is the number of successes. So R is equal to 4. Now if P is 0.07, what is Q? Well, we were talking about P plus Q is 1, so Q can be found as 1 minus P. 1 minus 0.7 is 0.3. So Q then is, Q is 0.3. And you know that P is the same as big P of S. That is the probability of success. Probability of success is what this is. Probability of failure is what that is. All right, just to get the notation straight. Now, we would like to find this probability number. Well, let's see. We know that we have a situation where we've got some coefficient, and we have, let's see, R is the number of successes. 4 successes, so it's going to be P to the 4th power Q to an exponent that with 4 needs to add up to the n. You see that we got 10 trials, so that's our n. So 4 plus 6. Okay, good. So we have a 4 and a 6 here as the exponents on P and Q. That's part of the battle. Another part is this coefficient. It's a combination of 10 things taken 4 at a time. And so away we go. This combination is 10 factorial over 10 minus 4 factorial times 4 factorial, whatever that turns out to be. And then P is, let's see, P is 0.7. And it's raised to the 4th power. And then Q is 0.3. And it's raised to the 6th power. And then when we punch this into the calculator, we find out that this turns out to be this. So here's the probability of 4 successes on 10 trials, given that the probability of success is 0.7. Here's another one. Same idea, a little bit different notation, and that's what we want. One of the things we want to make sure we're comfortable with. 8 trials here. That means n equals 8. The probability of success is 0.15. Now, probability of success is the same thing as lowercase p. So this is that. What about the probability of failure? Probability of F, or the Q value. Well, if P is this, then Q is this. And we just take 1 minus that to get the Q. All right, the number of successes is 3. That means R is 3. The probability of 3 successes means the same thing as the probability that R equals 3. You see, they say exactly the same thing. All right, if we're doing this sort of by hand, that is, we're doing it in a manipulative fashion like we did before, then we would think in terms of, we have a coefficient, we have factors of P, factors of Q involved. And how many factors of P? Well, P is the successes, so we have 3 factors of P. And out of a total of, remember, 8 trials now, so Q has how many factors? Well, let's see, 3 plus something is 8. Oh, that's 5. So these must add up to the n, or the 8, the number of trials. And now the coefficient is a combination idea of n things, 8 things, taken 3 at a time. And then again, away we go. We have the 8 factorial over 8 minus 3 factorial times 3 factorial. Then the p-value is this, and it's cubed. The Q value is 0.85, and it's raised to the 5th power. And when we multiply these out, we get 0.84. Okay, good. Now, you might be delighted to know that there are 2 other ways that we can make this calculation. It turns out there is a table in your textbook in the appendix, or one of the appendices in your textbook, that will give information about p-values and r values and n values and correlate all of that kind of thing. And we're going to look now at the table, and we're also going to look at a way to use the calculator to make the calculation as well. Here's a shot of the table in the appendix of your text. Notice that in this column we have values of n. Here's 8, here's 9. You can't see the other values of n on camera right now, but this is a column involving values of n. Now, we were talking about an n of 8. Now notice R, the number of successes, correlated with this number of trials 8, 0 through 8. And then the p-values are listed along the top here. Here's the p, and these are the values of p, and they go on off screen here. But we were looking at a p-value of 0.15, and let's see, n is 8, and the r value 3. So we're going to cross-reference the notion of this 3. We're going to slide over until we're under the 0.15, and that gives us the 0.084 that we found earlier. The calculation is made on the graphing calculator by entering a menu that is designated DISTR. It is the second function on VARs. So second VARs will give us this menu, and we'll cursor down to, I'm going a little bit past it here, the binomial probability distribution function. That's what this means. This says binomial probability distribution function. All right, press enter. And now there's a certain protocol associated with this. We have to enter the information in a particular order. The first item of information is n, the number of trials that we're talking about. And in our problem, the number of trials is 8. Then we enter a comma, and now we want the number associated with the probability of success, the p-value. And that in this case is 0.15, and then a comma, and then the number of successes that we want to calculate. And close the parenthesis, press enter, and we have a very long decimal here, and it rounds to the nearest thousandths to 0.084 as we found earlier. In this problem there are 8 trials. The probability of success is 2/10, and the number of successes is less than or equal to 2. Less than or equal to 2. So R is less than or equal to 2. So the probability that R is less than or equal to 2 can be found like this by calculating the probability. Now, less than or equal to 2 means 0, 1, or 2. So it's found by adding the probabilities that R is 0, 1, or 2. So it's probability that R is 0 plus the probability that R is 1 plus the probability that R is 2. Now I'll tell you, and we'll look at the table and the calculator in just a second, but I will tell you that the value we're going to find in the table is this for 0 successes, and for 1 success, and for 2 successes, and the total is going to be 0.798. But we want to understand that the notion that we're talking about less than or equal to 2 means that we add the probabilities involved in what that meaning is, in R being 0, 1, and 2. So here's how we would use the table to find the same value. Using the appendix table to find the 3 probabilities, we would look under n for 8. And now we want R to take on values 0, 1, and 2 for a probability of 0.2. So we're sliding over, we're correlating the R with a probability of 0.2. And here's the R of 0, 0.168, an R of 1, and an R of 2. And these are the items that we added earlier for our answer. The calculator is particularly handy in helping us with this problem because not only can the calculator calculate individual probabilities for us, it will accumulate probabilities up to a point for us. For this problem, we would press the second VARs and get into the desired menu, then cursoring down. Let's take a look at a couple of options here. Now we're going to access this A option. We've accessed this option before. This is the binomial probability distribution function. This can be thought of as the binomial cumulative distribution function. We are accumulating probabilities up to a certain point. Pressing enter, we'll enter the n value, 8, followed by a comma, then the p, the probability of success, 0.2, comma, and then we want to accumulate probabilities up to an r value of 2. That's what this means. Pressing enter, we get this long decimal. Now notice that if we were rounding to the nearest thousandth, we would get 0.797. And before, we were talking about an accumulation of probabilities being 0.798. That difference of 1,000th occurred because of a rounding error in calculating the individual probabilities and then adding them. And so this is presumably a more accurate version for that sum. You may have noticed that the calculator is able to calculate sort of the sum of probabilities from some point like down. R is less than or equal to a certain value. But what if we're faced with a problem like this, where we have, let's say, 12 trials and a probability associated with success, and we want the probability that R is greater than or equal to a certain amount. Now, if we're working this algebraically, or if we're using the table, the probability that R is greater than or equal to 5 would be found by adding the probability that R is equal to 5 plus the probability that R is equal to 6 plus the probability that R is equal to 7 plus and so on up until we add the probability that R is equal to 12. So we would add all of those probabilities. Now, another way to approach it, and a way that really makes the calculator useful in this situation is like this. We can say, well, the probability that R is greater than or equal to 5 is the same thing as 1 minus the probability that this doesn't happen. You see, what's the probability that this does not happen? If R is greater than or equal to 5, what's the antithesis of that? Well, it's the probability that R is less than 5. So 1 minus the probability that R is less than 5. And this is really what the calculator can calculate well. Now, remember, the calculator calculates from an R value to 0. So it's a less than or equal to idea. So really, we want to think about this for the calculator's purposes as 1 minus the probability of R being less than or equal to 4. And we're going to work this on the calculator in just a moment, but after we do that, I encourage you to work this using the table and make sure that you get the same result. We begin on the calculator by pressing 1 and then minus. And now we would like that accumulated probability up to an R value of 4. So we'll go second vars to get into the appropriate menu and cursoring down to this accumulation type of function, this one at the letter A. And now we want to enter, let's see, the number of trials is 12, followed by a comma. The probability is 0.4. Probability of success is 0.4, followed by a comma. And we're going up to an R value of 4 because R was less than or equal to 4. And closing parenthesis, pressing enter. Here is the probability that, actually this is the probability that R is greater than or equal to 5. That truly is what we're calculating here, and we did it in a rather offhanded way in order to use this accumulation idea within the calculator. Take a look at the information in this problem. A research team at Cornell University conducted a study showing that approximately 10% of all businessmen who wear ties wear them so tight that they actually reduce blood flow to the brain, diminishing cerebral functions. That just amazed me when I first saw this problem. At a board meeting of 20 men wearing ties, what is the probability that, and we're going to figure a probability in a moment. Let's organize our work though. We know that we're talking about 10% wear ties too tight. So that means the probability of too tight is 0.1, or the p-value for our purposes is 0.1. And the q value therefore is 1 minus 0.1 or 0.9. The fact that there are 20 men involved means that N, the number of items or the number of trials or however we'd like to look at it, is 20. Let's figure the probability that at least one tie is too tight. So we're figuring the probability that at least one tie is too tight, or the probability that R, the number of successes, if you can call a tie being too tight being a success, We want the probability that r is greater than or equal to 1. And the direct way to work this then is to take the probability that r is 1 and add the probability that r is 2 and the probability that r is 3 and so on all the way up to adding the probability that r is 20. The indirect approach makes more sense here, and it is that we're going to calculate 1 minus the probability that no tie is too tight, or 1 minus the probability that r is 0. Now, for the probability of an r being 0, we can either look in the table or we're thinking about 1 minus, let's see, no successes means failure, 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 you see, to the 20th power. 20 failures in a row, or it is 0.9 to the 20th power. So it's 1 minus 0.122, or 0.878. What is the probability that more than 2 ties are too tight? More than 2 are too tight. So that's the probability that r is greater than 2. And we would find that sort of indirectly, but the smoothest way to do it is 1 minus the probability that r is less than or equal to 2. Now, less than or equal to 2, for the probability of r to be less than or equal to 2, we would add the probability that r is 0 with the probability that r is 1 with the probability that r is equal to 2. So adding those three probabilities and then taking that sum and subtracting from 1, you see, is the way the calculation is performed. Of course, another way to work this is to use our calculator, and I think we know how to do that. This is not a particularly difficult problem to use the calculator on, and I'll leave that for you to do on your own. But at any rate, it's 0.323 as the probability that more than 2 ties are too tight. Now notice that that's almost 33%. It's like a third then of the people, or there is a 1/3 probability, just about, that more than 2 ties are going to be too tight in this room of 20 men. The next part says, what is the probability that none are too tight? The probability that no ties are too tight. That means the probability that r is 0. That would be failure, 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 failure. We actually talked about this before as part of another problem, but q to the 20th would be 0.9 to the 20th power, or let's see, 0.122. What is the probability that at least 18 are not too tight? Now, this is an interesting aspect of some problems where we're not actually looking for a success idea. We're actually basing our question on failure, not too tight, you see. And I think if we're going to use the table, we would like to restructure the problem and think of it in terms of success. If at least 18 ties are not too tight, that translates into no more than 2 being too tight. So we can think of the probability that not more than 2 are too tight to make the calculation. And that's the probability that r is less than or equal to 2. And that would just be the sum of these probabilities. The probability that r is 0 plus the probability that r is 1 plus the probability that r is 2. And we can simply read these numbers off of the table and add them to get our answer.